I'm not sure. Hey guys, can you hear me? Oh, okay. All right. So yeah, I guess welcome to this class, which will just be kind of a review session so we've prepared some sample problems that are basically like the exercise sheets, and they're representative of what might be on the exam. And so Hassan and I will kind of just go through them and show them to you, and then we can solve them basically together. So yeah, are they actually online yet, or this is just?
So the questions.
Yeah. So what do you want?
I think they're not yet online, but they will be online.
Yeah, so we'll go through these questions in class, and they're not online just yet, but they will be online later. So if you guys follow through here, then you can look at them again yourselves afterwards. And okay, how do you actually change this thing?
Can you hear me without using the mic?
Yeah.
Oh, okay.
Sort of.
So after the review session, we will release both the questions and also the solutions for them on the website, so you can check them later.
Yeah. Okay. So can most of you guys read the overhead, or is it too small? Especially in the back? I don't know. It's okay? Yeah. Okay. So I guess we'll just start going through these then. So the first question asks about a full pipeline processor. So basically, I'll just read the question. So keeping a processor pipeline full with useful instructions is important to achieve high performance. And so what are 3 fundamental reasons why a processor pipeline cannot always be kept full? So we went over this in lecture at some point, and so I don't know, do you want time to think about it? Or I guess this is really however you guys want to do it. So Hassan, do you have a pen? Do you have a pen? Oh no, I have it. I have the pen. Okay. That's right. Yeah, data dependencies. That's absolutely one of them. So we have. Okay, another one. Yeah, go ahead. Yeah, that's right. So that counts as control dependencies then. So data depths and control depths kind of go together as one reason. Yeah. Okay, another one. Yeah.
Not only instruction use for the stages of the pipeline.
Yeah, that's right. So the example there was where you have an add instruction that just takes a couple instructions, or maybe a multiply which takes many. And so when you have to push them both through the same pipeline, then they take different amounts of time. So that's basically multiple cycle operations. And then can you guys think of one more? So, yeah, go ahead. Sorry, could you repeat that? Oh, yeah, that's right. So actually, I guess this question is really asking about steady state once the pipeline's full. So that's true, but that's not, I guess, what this question is asking about. Yeah? Yeah, that's absolutely right. Yeah, so resource contention. Yeah, so these are 3 pretty good reasons why pipelines don't always go 1 per cycle, right? So, okay, so the next question is about out of order and data flow. So when we talked about data flow a little bit, we said that it's kind of like a different paradigm than just an in-order processor. And so the first question asks, so when exactly does an instruction execute in a data flow processor? So if you've implemented a program as a data flow graph, when does each node begin executing? Yeah, go ahead.
As soon as the data dependencies are.
Yeah, so the data dependencies meaning what in this case? So
If I have a MBA, as soon as we have both A and MBA, we can
yeah,
that instruction.
that's right. So we can write this as when the inputs to the data flow node are ready, right? So in this case, the instruction executes as soon as the inputs are ready. Okay. So then the second part is, when does the fetch of an instruction happen in an out-of-order execution processor? So this is no longer a data flow graph. This is just a regular out-of-order processor. So what determines when an instruction gets fetched here? Do you guys have any idea? Do I just say it? Yes. Okay. Well, I guess for this one, it's basically like, so you're executing a sequential program, right? So this is all PC based, and so your compiler has generated a series of instructions that are executing one by one on this processor. So in this case, regardless of when the inputs are ready or not, you execute the instruction when the program counter reaches the particular instruction, right? So it's entirely determined by the control flow and when the PC reaches that instruction. So the fetch is determined by when the PC reaches that instruction. And so the major difference there is that you don't execute as soon as your inputs are ready, but you rather have to wait for the control flow to reach that instruction instead. Okay? And then the third part of this question asks about, in this out-of-order processor, what structure holds the instructions until they are ready to execute? Because you still have to wait for the instructions dependencies to be resolved, right? The input operands need to be ready before you can begin execution. So what structure is that called? Yeah? That's right, yeah, it's a reservation station. Okay, yeah, so the instructions wait in the reservation station until all of their input operands are ready, and then execution begins. So for the next question, we have an example of some reservation stations, and we're asking, okay. So here's basically a set of reservation stations for an add functional unit and a multiply functional unit, and this is during some point throughout execution at a particular cycle. And all the x's are values that we just don't know. So the question is, what's wrong with this picture? Because this isn't a reasonable state of execution. So can you guys figure out what's wrong? I don't know. Yeah. Like, yeah, so... Okay, go ahead.
There is a cyclic dependency. So tag A depends on D, D depends on C, and C depends on
Yeah, so that's actually exactly right. So I guess let's go through this a little more step by step. So what he said is that there's a cyclic dependency between some of these guys, and so they won't be able to execute. And so if we look at this, we see that, so if we consider each tag as a different instruction, right? So let's say here. So we have A depends on tags D and just nothing there. It's not waiting on something. So A depends on D. Then tag B depends on tag E, right? And then tag C depends on both B and A. Tag C depends on B and A. And then for the multiply, we have tag D, which then depends on B and C. And then we have tag E, which depends on nothing and B. So for one, if you look at these two particular instructions, then we have B depends on E and E depends on B. So that's a cyclic dependency, and neither of these instructions will ever be able to execute because they're both waiting on each other. And so this processor will just be stuck in deadlock, right? And it won't ever execute anything. If you look at the other instructions here, we have A that depends on D, but D in turn depends on B and C, but C depends on B and A. So again, we have a cyclic dependency between A, D, and B and C. So A, D, and C in this particular case. And so that's another dependency that's not ever going to be resolved, and so this processor will be stuck, right? So the problem here is deadlock due to cyclic dependency. Okay? Are there any questions about that one? I don't know. Not so much? Okay. So we'll go to the next one then. So the problem is this whole thing won't fit on the overhead. It's too small. Maybe. I don't know. So this is a longer, more extensive question about out-of-order processing where... Can you like literally raise this? No. But I think it's already at maximum. Is it? You locked it, right? You locked the focus. How do you unlock it?
It's not
Or-
about the focus.
Oh. Okay. What do you want to do? Do you want to try and see if you can get the projector working? I can go through. So okay, so he's going to try and get this projector working, so he can put it on the like you show the actual PDF. But so here, this question details out of order execution, and so what happens is here we give an example of an out of order execution state. So down here, real quick. So we give you an example of what the register alias table looks like and 2 reservation stations. And so the question has a bunch of different parameters here. And we detail what the system is like and what all the different things are. And then the question is to determine which 5 instructions are actually executing in this system right now. And so if we go through the system constraints real quick. So for the first one, we have a single cycle fetch and a single cycle decode. And the machine can fetch 1 instruction per cycle and decode 1 instruction per cycle. Okay? Then we have that the machine dispatches 1 instruction per cycle into the reservation stations in program order. So that's in order dispatch. And this occurs in the same stage as decode. Then the instruction always allocates the very first reservation station that's available in top to bottom order at the required functional unit. So if we have the reservation station here, you're always going to allocate the first available entry. Then when a value is in the reservation station or it's being written back to the register file on the machine, the old tag that is in the register alias table is not cleared. So did you? Okay, yeah, so we'll just go through it like this. Sorry about that. But yeah, so the old tag that's here after broadcast is not cleared. So this remains. Then we have that after the instruction in the reservation station finishes executing, the reservation station is cleared. Then both the adder and the multiplier are fully pipelined, and an add takes 2 cycles and a multiply takes 4 cycles. And finally, once an instruction completes execution, it broadcasts its result, just like in the Tomasulo algorithm, and any dependent instructions that are waiting for that result can begin executing, assuming that all the other operands are also available. So here's the state again. And so we're given that the machine is initially empty, so it starts out with nothing executing. Then 5 instructions are fetched and decoded and dispatched into the reservation stations, as you see right now. And this is the state of the machine after the first instruction has executed. So your job, again, is to determine which 5 instructions have executed and what they are in program order. And so I guess in terms of the solution, it looks like kind of like you have to fill these out, where give the 5 instructions that have been dispatched, and you put it in the form of opcode, destination register, source register, right? And so we're given that there's 5 instructions here, and I'm not sure how to fit this all on the overhead. So here's the state again. I guess if you guys want to take like 5 minutes or so to actually do this on your own, I think it'd be a very helpful exercise, because I could just give you the answers, but then that's not really helping you go through it, right? So yeah, give it a shot, and then in like 5 minutes, we'll go through it together and see how to do this. All right, hey guys. So I guess it's really hard to go through this without like being able to read the top part of the text. So I think we'll just go through it. So we can just go through this example. So again, the problem here was to figure out the 5 instructions that are executing here, right? And so the first thing that we see is that, so we know that 1 instruction has already executed, right? So it's complete. And we know that because over here it said that after an instruction's finished executing, the relevant reservation station entry is cleared. And so since they're also allocated from top to bottom, we know that there should have been 5 instructions in the reservation stations, but since one's completed, it's gone. And that had to be this X right here, right? Because it's already been cleared since it's finished executing. And so we know the first... Oh, is that? Okay. Okay. Zoom still doesn't work. Okay. Yeah, so So okay, right here. So this X, since it's missing, that's the instruction that's completed execution already, right? So we know that this is in the multiply unit, so it had to be a multiply instruction. So it's mul something, something, something. And so now we need to figure out what the operands of this guy were. So we know that X represents a tag for the destination register, right? And so when it was allocated, when the instruction was when the instruction was first scheduled, it went through the register alias table and got a tag for the destination register. And since this instruction has tag X, and tag X is in the register alias table, we know that the destination register should have been register 3. And because the valid bit is set to 1, we know that this instruction has completed execution and it's already broadcasted its result. So we know this is a multiply to register R3. And so we need to figure out the source operands. And so given that register X, in instruction number X here, it initially had 2 sources that have finished executing. And so in the reservation stations overall, we see that X is used over here, right? So instruction A is dependent on the result of this instruction X. And so X represents a destination register, which is now valid because it's been broadcasted, and it contains the value 500. And you can see the same data in the register alias table because it's the same broadcast, right? So we know the result of that instruction was 500. So this R3, this multiply instruction, resulted in the value 500 being in register 3. And so since this is the very first instruction, and we're guaranteed that no instructions were here before the program began execution, we know that something had to happen where a multiply resulted in the number 500, given the previous architectural state. And so by looking at the original value of the register file, we can see that really the only way to generate the number 500 is by doing a multiply between 50 and 10, right? So 50 and 10. And so the source operands for this multiply had to have come from these 2 registers. And so we know this is R1 and R7. So this multiply had to take in R1 and R7 and put the result in R3. And then we have the first instruction, okay? Yes?
Depending on what the original value of R3 was, it could have been something else. Well, it could be R3 was 25. And then we could have R0 and R3 as well.
Yeah, that's true, right? So if R3 previously held like another instance of 10, then it could have been a source operand because it was overwritten by the destination tag. And the reservation station was cleared, so we don't know what was there. It's true? Yeah. So I think you're right that it could have also been there. And so that's also a solution. So either R1 or R7 could have also been that, or some other combination of something that could produce 500 using the result of a multiply. Yeah, that's absolutely right. Okay. So this is the first instruction, which could use either these registers or R3, as previously mentioned. And that's not true for the other registers because their valid bits are set to 0, right? And so those values haven't been overwritten yet. So these are the original register values that were before the program was loaded in. Okay. So now we have to determine what the second instruction was. And so we have a couple of pieces of information to help us determine that. So first we know that when the reservation station entries are allocated, they're allocated in order top to bottom, right? So the next instruction that was added to the program either had to be instruction A or had to be instruction Y, right? Because they're allocated top to bottom and the state was clean before this program was loaded in. And so then we're trying to figure out which one of these is the next instruction. So if we look at the multiply, we see that the multiply over here has no dependencies on any other tags. And so basically the values it's using, it can begin execution because it's not waiting on any of the other instructions to actually start. However, if we look at instruction A, we see that its source operands are dependent on tag X and tag Y. However, if this was truly the second instruction, we would not have a tag Y because there's only been tag X so far. So there's no possible way that instruction A was actually the second instruction in the program. So therefore, we say that it has to be instruction Y, and so we know that the second instruction is another multiply. And this multiply results in Y, which if we look in the register alias table corresponds to register 4, right? So the destination had to be register 4. And so now we have to figure out what the source operands are. And because they're not dependent on tags, they can't be the result of previous instructions, and therefore we need to look for registers that had 50 and 37. And we see that's R1 and R2, right? So we say R1 and R2 are the source operands. So the same argument that was mentioned earlier also applies. So since R3 was overwritten when X committed, we don't know what was previously in that register, and it could potentially have been one of these values as well. But for now, we're just going to assume that R1 and R2 are the ones that are okay as well. So now we have the first two instructions of the program. And so we just repeat this process again to figure out the third. So the third possible instructions are A and Z here. So either A and Z are the next possible instructions. And so by using the exact same argument again, we see that A depends on X and Y, both of which have been seen, but Z depends on A and B, neither of which have been seen yet. So Z could not have been the next instruction. So we know that the next one is A. And so A is an add. So we know the next instruction is an add. Okay? And so again, this add, we can look in the register alias table to figure out what its destination register was. And so in this case, we have R2. And for the source operands, we see that the tag X and the tag Y are the two registers that it's trying to read from. And since X and Y, we know, represent R3 and R4, this instruction should have been add R2, R3, R4. Okay? And so then it's down to figuring out what the last two instructions are. And so at this point, we have X here, we have Y here, and we have A here, right? So we have a B and Z left to allocate. And so since Z depends on A and B hasn't been seen yet, B must have been the next instruction. So we have B, which is another add. And B, so to figure out the destination register, we go look it up in the register alias table, but we see that B doesn't exist. And that's only possible if the instruction hasn't executed and it's been overwritten by another instruction that also aliased the same register to a new tag. And since Z is the only one that's left to execute, that means this entry for R6 is where B used to be, but then when Z was scheduled, the register R6 was aliased again and took on the tag Z. So we know that both of these instructions have the same destination register. So here we have the destination register is R6, and the source operands of B are whatever has 20 and 17. And so we have R0 and we have R5. So R0, R5. And then that leaves us with our last instruction, which is tag Z, and that's a multiply. And we see that it's to R6. And the source operands here are A and B, right? And the result of A is R2, and the result of B is R6. R2, R6. So there we have our 5 instructions that were originally in the program. And this is the correct order in which they were supposed to execute, right? And so basically, given any valid state of what these 3 structures are, you should really be able to reconstruct the original instructions just like this. Yeah, go ahead.
We change the instructions of add, so A and B, so switch them.
Sorry, you're saying these are switched here? A to R2, A is the add to R2, B is the add to R6, right? What do you mean by they're switched? It's fine, right? Yeah. What's the problem? I don't see the issue. Yeah, that's right, in top to bottom. So this was allocated before this. So A had to come before B in program order, right? Okay. Okay, yeah, cool. Any other questions? Yeah, go ahead. Yeah, this R6 right here. So the way we determined this was by knowing that this instruction was the 4th one to execute, which we deduced by going one by one through the instructions. And then every destination register is basically aliased by this tag, right? Either A, B, C, X, Y, Z. But B doesn't exist in the register alias table at all. So we don't know what the destination register was. But in this particular example, there was only one place it could have possibly been, because A, X, and Y were already allocated. Those are previous instructions. And since B did not overwrite those, and it's not in any of the empty spaces, B had to have been in R6, because there's nowhere else it could have been. And since we have an instruction after it Z, Z had to have overwritten B. Like, there's no other potential solution. in this example. Yeah. Okay, yeah, go ahead. So we see that in R6, the valid bit is 0, right? And that means the data is old data, like it's stale data from some previous computation that is not the updated value. Yeah. Yeah, but B hasn't executed yet, right? It's still in the reservation station. So after it executes, then yes, it would broadcast the value 37 along with the tag B, and then anywhere that exists would be updated. Yeah, it just has not executed yet. Yeah, is that another question? So that's a great question. So this is the register alias table, right? Which is different from the architectural register file. And so in here, we're simply keeping track of the very latest tags that we have and what tag represents which register. But the reorder buffer that puts all these instructions back into order for retiring the program, that's where you would write this value in. And so the reorder buffer also contains an entry with tag B, and that hasn't been overwritten because it has a dedicated slot in the reorder buffer. And so when this instruction executes and it broadcasts, it will update the value in the reorder buffer, which will then retire the instructions in program order again. Yeah. So this is, the speculative state. Okay. Any other questions before we move on? Okay. So the second part of the question, part B. So now we have a timing diagram. And so we're saying, so we assume that the machine has cleared out all of the instructions and it restarts execution from the beginning. So now we want to show the full timing diagram for the sequence of these 5 instructions that we determined, right? And so we're going to basically make the assumptions that this guy states. And so we assume that the machine stops fetching after the 5th instruction, and it's just executing these 5 instructions that we have. And so just like we went through like in some of the class examples, we're going to use F for the fetch stage, D for decode, E1, E2, E3, E4, blah, blah, blah for execution, and then W to signify write back, right? And so we're basically trying to figure out how many cycles it will take to execute this program. And so given the instructions, this is really nasty. Okay, it's good. Okay, so let's start with the first one then. So we basically, this first instruction that we determined was the multiply. So this was the mul into R3 of R1 and R7, right? So that was our first instruction. And so in the original text here, we were given that multiply instructions take 4 cycles, right? So we know that there's going to be 4 execute cycles in order to make this computation. So, so here, actually. So the first cycle is going to be spent fetching this multiply instruction, right? And because the machine has just started, there's nothing to block that from happening. So we fetch the instruction, we decode the instruction, which again, in the text, it said that when you decode an instruction, it also puts it in the reservation station. So we have the fetch and the decode, and then the multiply takes 4 cycles. So we have 4 execute cycles, E1, E2, E3, E4. And then after that's complete, we have a write back, right? And so the multiply instruction takes 7 cycles total. Then we have the second instruction, which is the mul R4, R1, R2. And so, again, this instruction is not dependent on the previous instruction or any previous instructions at all. So we don't have to wait for any of the source operands to be ready before we begin execution. We just have to wait till we have the resources available. So fetch, on the next cycle, when the fetch is available, we fetch, we decode the instruction, and since the functional units are fully pipelined, so again here, it says the adder and multiplier are fully pipelined, right? Which means we don't have to wait for this execution to finish. We just have to wait for the first execution stage to be empty. So we can begin executing E1, E2, E3, E4, and write back is also free, so we can go ahead and write back that instruction. Then we have the third instruction, add to R2, the source, R3, and R4. So this is a little more complicated because it uses the results of both the multiplies. And so we can go ahead and fetch this instruction, decode this instruction, but we can't begin execution yet because the source operands aren't ready. And so this instruction is currently sitting in the reservation station, and it's waiting for the broadcast so that it can begin execution. So we can't do anything until R3 and R4 are ready, and R3 is ready after here. R4 is ready after here. So we have to wait until that result's done and the broadcast happens. So we can do nothing here, and then we can execute here. Yeah. And so adds this time take 2 instructions. Add instructions take 2 cycles. Add instructions take 2 cycles. So there's E1, E2, and then we have a write back. So that's the first 3 instructions. Then we have an add to R6, which consumes R0 and R5. Sorry, was there? Yeah, go ahead.
Are we assuming, or does it say, I don't know, does it say in the top that we have forwarding in this case?
That we have forwarding. So, yeah, this says, I think it said that the broadcast happens right after the execution is complete. So when an instruction completes execution, it broadcasts its results. And dependent instructions can begin execution in the next cycle. Yeah, so it's not forwarded in the very last cycle, right? You have to start the next one. Okay? Yeah, so if it was just forwarded straight from here to the next functional unit, then this E1 would have begun here, right? That's what you were thinking? Okay. Right. Okay, so this add instruction here, R6, R0, R5. So R0 is not a previously written register, and neither is R5. So we can just go ahead and execute this without any control dependencies. Data dependencies? Not sure. Okay, so fetch, decode, we go ahead and do. And the adder is currently, the adder is currently free, so we can immediately begin execution because we have R0 and R5. So we do execution 1 and execution 2, and we are unable to write back here because the write back stage is busy writing back the result of this multiply. And so we have to stall, and then we write back here. Okay? Then we have the final instruction, which is a multiply. And so we multiply into R6 the value of R2 and R6. So R2 is dependent on this add. R6 is dependent on this add. So both of these, neither of these source operands are ready right at the beginning. And so we go ahead and fetch and decode our instruction, but we cannot begin executing the multiply immediately until both results are in. So the R2 is ready after this execute stage, and R6 is ready after this execute stage. So we can't do anything until they're both ready, and then we can begin execution. So we have execution 1, execution 2, 3, 4, and then we have a write back. All right, so that's the execution timeline of our 5 instructions. And we see that in order to do the whole in order to do the whole thing, it takes us 14 total cycles. Yeah? So, okay, any questions about that? Yeah. Yes. So then the multiplies are these and these, and so here we can't start on the same cycle as a different multiply, but we can start a cycle later because it's fully pipelined. And here there's nothing else going on at all, so it's free. Yeah, I think you had a question? Yeah.
Instruction 2 and instruction 4 are finished at the same time with executing. Is it clear which instruction is going first to the write back, or change these two?
That's a good question, actually. It might say that the oldest instruction gets priority. So the actual write back, so the broadcasts would have to be ordered if there's just one broadcast bus. And so there would be some sort of arbiter that decides which one goes first. But you definitely can't do the write backs at the same time because you have to write back in program order, right? So you can't write back on the exact same cycle. As far as which one broadcasts first, that's down to the implementation. And so if there's nothing defined here, then it really depends on the particular implementation. Yeah, when multiple instructions are ready to execute, the oldest ready instruction is chosen. Yeah, so in that case, that could help you resolve that confusion. Yeah, go ahead.
Just to verify that, when you say the oldest is chosen, so only one is broadcasted, and so only one can take the next step for executing the next time?
That's right. So in this particular implementation, at least, so there's only one bus that connects to everything. And so when somebody decides to broadcast on it, they're sending their particular value along with the tag to every device in the, to the reservation station, to the reorder buffer, to everything. And so two different parts of the system can't do that at the same time because there's only one bus. Yeah. Yeah. Yeah, that's right. So some of them would be held back. Like the actual broadcast would be delayed. So the functional unit would stall, and then it would broadcast at a later point in time when the bus is free.
And one more question, because when you were looking at the multiplier right after the multiplier, you looked up your instruction sheet, and there it said it's fully pipeline, and therefore they can run in parallel.
Mm-hmm.
And then when you came to the error, you checked whether because there it also says it's fully pipeline.
Yes.
So it means you can also have two errors running at the same time as long as the execution doesn't start at the same time.
Yes, that's right. You can have one per cycle. Yeah. Okay. Was there some? No? Okay. Any more questions? Oh, yeah. Yeah, go ahead.
In the lecture, some of the times we have memory that we can write to two values at in the single cycle, and our readers tells that this does not exist unless it's explicitly stated in the exam.
Yeah. So that should be very explicitly stated if that's the case. Yeah, you shouldn't have to worry about that. I mean, if it's very unclear, then you can probably ask about it. But yeah, that should definitely be specified. Yeah.
My intuition would tell me that we have to write the instructions back in order, so I would wait to write instruction 4 back until after the write back of this.
Oh, yeah. This one right here, right? Yeah, I think that's actually right. I think I made a mistake there. So you absolutely should be writing back in program order. So this should be delayed until there. That's right.
So I think this right version is not really the right back.
Okay.
Before it's reorder, it's actually broadcasting the volume.
So it says, yeah, right back. Okay. Yeah, so if we're talking about the commit to the architectural state, then it should definitely be in order, and it would be delayed like this. Yeah, that's right. Okay. Does that make sense? Okay. So be good with that? Okay, so I'll move on to the next part then. So the next part asks to show the state of these guys after 8 cycles, right? And so we have to fill in the state of the register alias table and fill in these two reservation stations, what they look like 8 cycles later. And so when we had this example, which was given to us as part of the problem, this was after the first instruction finishes executing, right? And so by looking in our timing diagram here, we know that it finishes executing right at cycle 6. Yeah? So this state here is given right after cycle 6. And so we need to take this state and propagate it forward to 8 cycles. So after 8 cycles. So whatever happens in cycle 7 and 8, we have to update this diagram to reflect that. And so here we can look at what's happening. So for the first one, the first instruction, the multiply. So the multiply has already finished executing, which means that over here, it's already cleared its entry here because it's already done its broadcast. The register alias table has been updated, and all of the other references in the reservation stations have also been updated. So nothing changes there after cycle 6. For this instruction, the multiply, so it's in the process of executing. And so that means that it hasn't done its broadcast yet. It's still sitting in the reservation station here, and the tags haven't been updated. That's like halfway? Okay, yeah, I guess so. Okay, I'll finish going through this, and then we can take the break. So by cycle 8, we see that this actually finishes executing, meaning that it will go ahead and do its broadcast, and so we have to update the state of this to reflect that broadcast. For the add instruction, it hasn't even begun executing, and it won't begin executing, so nothing's going to change. For this add instruction, it actually does finish executing, and so it will do its broadcast, and so we have to update the state to reflect that. And for the last instruction, nothing. So basically, we only really have to worry about the broadcasts of this instruction and this instruction, right? And so we can go ahead and start doing that. So we know that over here, the second instruction, the second instruction was a multiply to R4, so that's tag Y. And then this instruction, to add to R6, is tag B. So these guys are the ones that will complete and do their broadcasts. So let's update the register alias table along. So yeah, I guess we kind of have to do these all at the same time. So we know that what's changing is tags Y and B. So if we go through this reservation station here first, we see that tag X is still going to be empty because it's been deallocated and it hasn't been reallocated with any new instructions. Y completes its broadcast. Okay, so that means its reservation station entry is cleared. And so this reservation station will also have nothing for Y anymore. Okay, Z has not begun executing. So Z hasn't completed execution, so its reservation station entry remains. So we still have here A0 dash, but B has actually completed and it's committed its broadcast, right? So B is still tag B here, but it is now valid because it's done its broadcast. And we actually have a value. And so we have to kind of figure out what that value is. So we saw here that B was actually an add instruction between the values 20 and 17. So that results in 37, right? So we know that over here, this B results in 37, okay? And so that's what happens after B finishes and does its broadcast. And we can go ahead and update that in the register alias table as well. So we know that B was this instruction, which was adding to R6. And so R6 would be where the tag B used to be before it got overwritten with Z. And so when B now does its broadcast, it will broadcast to all three of these structures. Anywhere where tag B matches, it will update the value. But because it got overwritten by Z here, it no longer matches anything in the register alias table. So during this broadcast, nothing gets updated at all. So the register alias table is the same in terms of B's broadcast. But we also had instruction Y, which completed. So Y also does its broadcast. And so Y was the instruction that does the multiply of R4, R1, and R2, right? So here, the multiply is of 50 and 37, which results in a rather large number. What was the number? Yeah. This is, 1850. Okay. So the result, so the Y basically, when it completes, it broadcasts the pair Y and 1850 to the rest of the structures in the system. And so anywhere we used to have a Y, it becomes valid, and the value becomes 1850. And so we have that here, and we have that here, right? So, sorry, Y becomes 1850. So we have to reflect those updates in the new architectural state as well, the new speculative state. So here's the register alias table, which we're going to update. So R4 is now valid. It had the tag Y, and it's 1850, right? R6 hasn't changed because Z hasn't moved anywhere. A also has not executed. Because, so A also has not broadcasted. So A in R2 is still invalid, and the old data remains there. X has broadcasted at this point. And it has, so it's already propagated its values everywhere. It's already valid. So X remains 1, X 500. And the other values haven't moved anywhere because nothing is read or written to them. So they're just exactly what they were before. 1 no tag 20, 1 no tag 50, 1 no tag 17, and 1 no tag 10. Right? And so all we have left is this final reservation station, which represents the reservation station for the add. So at this point, instruction X, which is the first instruction, it has completed its broadcast. This is instruction A. So instruction A, which looking back over here is the add R2. So that's this instruction. This one still has not executed, and it hasn't completed its broadcast, so it stays in the reservation station. And so A is still here. We have X 1 500, but Y is now valid, and it will remain like this until this instruction is finished executing and it broadcasts, at which point it will clear that reservation station entry. And finally, B we said has completed its broadcast, and so this entry is entirely deallocated, and so nothing's here. Okay? And so by going through that process, we have filled in the state of the register alias table and the reservation stations after cycle 8. And so we could go ahead and repeat this process for whichever cycle we want, right? Because we can compute the architectural state at any point in time, given that we know how everything executes. So that's it for this question. Do you have any questions right before you guys break out? Yeah. Okay.
So at this point, we have completed instruction B, but we do not broadcast this value back to R6. Because otherwise we should have
So the problem is, so you're right, but Z came and overwrote that tag. And so B no longer exists in the register alias table. And so when the broadcast happens, there's no tag match anymore. And so you won't update the value. Yeah. So if Z hadn't come, then yes, you're absolutely right. We would have set it to valid and put 37 in there. But anywhere else that B does appear, exactly what you said would happen. 37 gets updated just like it did right here. Okay. Anything? Yeah, go ahead. Sorry, could you repeat that a little bit louder? Yes. So this thing is just keeping track of the current state of all the architectural registers for purposes of allocating new instructions. The actual value the actual value of the register is not being lost because it's stored in the reorder buffer. So as soon as an instruction is allocated, right, it gets an entry in the reorder buffer that's dedicated to just that instruction. So in this case, B, which got overwritten in the register alias table, means that for purposes of allocating new instructions, the very current state of register 6 is Z, which hasn't been computed yet. It's like a speculative value. But the actual value, the actual instruction that we're writing back, that's stored in the reorder buffer. And so when the broadcast happens, it'll be updated in the reorder buffer. And as the reorder buffer entries are retired, it'll get committed to the real state of the machine, like the actual register file. So the register alias table just keeps track of the current state for allocation purposes. And so it's okay to overwrite the registers there because it's just the current state. The actual value is kept in the reorder buffer. And that's the part that makes sure that everything retires in program order, right? And that nothing breaks, effectively. Yeah. So yeah, potentially we could ask you to show the reorder buffer here as well, which would add another level of complexity to this. But yeah, in this particular problem, that wasn't the case. Okay, yeah, any other questions? Okay, yeah, I guess you guys can take like a 10-minute break or something. Like, what, 10, 15? I don't know. We'll come back at 2:20, yeah? Okay.
Yeah. This example.
Can you sound, dude? Nah, dude. Nah. Yeah, hey guys. Are you ready for the, I guess, next round of questions? Okay, so I guess, yeah, so we'll go right into it. So the next set of the next question is about GPUs. And so I think it's a little simpler than the one Onur solved last time in class, but I guess, okay. Yeah, so this question deals with SIMD utilization, right? And so we define SIMD utilization as the fraction of SIMD lanes that are kept busy with active threads while the program's executing, right? So if you have a situation where some of the threads are doing nothing while the other threads are executing, then you have like not 100% utilization, right? And so we have this piece of code right here, and we're saying that this piece of code gets executed on a GPU, and every thread in the SIMD operation does one iteration of the loop. So here we have I is less than 512 times 1024 iterations. So every thread does one iteration. And so we assume there's no memory loads and stores. So A, B, and C are already just stored locally in vector registers. And there's a hint here that says there are 5 instructions in each thread. Okay, and we have that a warp in the GPU consists of 32 threads each, right? And there are 32 SIMD lanes in the GPU. So what we're doing here is we're taking this piece of code, and for all of these 512 times 1024 iterations, we're dividing it among a bunch of threads that execute each iteration in groups of 32. Okay? And so the piece of code here, which is 5 instructions, is basically doing an if condition on one of the elements of B, and then it does a multiply and then a bunch of adds. So we can say that this is the first instruction effectively, which is like a branch. And then we have an instruction here, instruction here, instruction here, instruction here. Right? So this whole piece of code is sort of the internal is 5 total instructions. So the first question asks us, how many warps does it actually take to execute this program? So, yeah, I don't know. Anyone want to take a stab at it? Nobody? Okay. So basically, so it's this thing again where we're dividing the total number of iterations amongst groups of 32. And since each warp consists of 32 threads, it's basically just the total number of threads we have to do divided by 32. So we just have like 512 times 1024 over 32, right? Which ends up being like 2 to the 9 times 2 to the 10 over 2 to the 5. It's like 2 to the 14. So we have 2 to the 14 warps, which I think was, what, 16K? Yeah, so we have 16K, which is like 6, 5, 5, 3, 6 individual warps, right? Wait, no, what am I smoking? So this is 16,384, right? Okay, yeah, so we have 16,384 warps, okay? And so that's the answer for that. So the second part asks that when we go ahead and try and measure the SIMD utilization here with a particular input set, we find that it is this magic number, 9 out of 40. So what does that tell us about the arrays A, B, and C? Okay, so again, the SIMD utilization here was defined as, the fraction of SIMD lanes that are actually doing useful work relative to the other ones. So we basically have some number for the SIMD utilization here, right? So if we know that one thread executes 5 total instructions, the SIMD utilization is essentially how many threads are not executing useful instructions, right? And so in this particular example, why would a thread not be executing useful instructions? Yeah. Yeah, that's right. So it's all about this conditional here. So in a warp, all of these threads execute in lockstep, right? They're all executing the exact same instruction at the exact same time. But if we have some sort of branch here where some of them are no longer executing the same thing, then they'll just basically be doing no ops while everything's going on. And so what will actually happen will be that there'll be some threads executing, and the ones that execute will do like all 5 instructions if this conditional is passed. But if the condition is not passed, then those instructions will simply execute the branch, and then they'll be doing no useful work here. And so in a particular warp of 32 threads, some of them will just execute the branch, and then some of them will execute the branch plus the inside of the branch code, like all of these instructions. And so we're being told that of all these instructions here, 9 out of 40 is the overall ratio of instructions being executed versus like no instructions effectively. And so one way we can think about this is that just out of the total number of instructions executed per warp, right? So if we know that a warp is 32 threads, each thread is going to execute 5 instructions, then the total number of instructions executed is 32 out of 5, right? Out of like the whole block of things. And so for the utilization to be 9 out of 40, that means some amount of threads that executed no useful work. So they executed just the branch, and some executed the full 5 code, the full 5 instructions. So we can say like we have, let's say, there's no room. Okay, let's say n is the number of threads that execute all 5 instructions, right? So we have n threads executing 5 instructions plus 32 minus n threads executing just 1 instruction, right? And so that ratio out of the total number of instructions executed, 32 times 5, is being equal to 9 out of 40. Does that make sense? Yeah. So we can go ahead and solve for what this n should be. And so we find that, 5n plus 32 minus n, okay. Yeah, so 5n plus 32 minus n over 32 times 5 gives you 32 plus 4n over 32 times 5 equals 9 out of 40, right? And so we solve that for n. What do we get? So we have, this is 8 times 4 times 5. So this is 40. So we have 8 times 5 is 40. This is really out of 4. So this is just 1 then, right? Yeah, and it's just 1. So we're basically saying that there's only one warp that is executing all 5 instructions. So one thread. There's one thread out of the warp that is executing all 5 instructions. And so that's basically the worst possible case, right? Because if we had 0 threads executing all 5 instructions, then all of them would just execute 1 instruction, and then the warp would be finished, and SIMD utilization would be 100%. Or if all of them were executing all 5 instructions, the utilization would again be 100% because they would all execute all 5. But here we have like pretty much the lowest possible number we can have. So what this tells us is that out of every group of 32 elements of B, only one of them actually passes this conditional, right? So for B, we can say that for BI being less than 0, so only one out of every 32 group in B is greater than or equal to 0. Is negative. And then it passes. You want it to fail the conditional. So it fails the conditional if BI is greater than 0, or greater than or equal to 0, right?
Only one passes, the other fails. Only one out of
Yeah. So in this case, it's 9 out of 40. So only one is actually, okay. So it's less than 0. Yeah, so only 1 out of every 32 group is less than 0. That's what we can say about B. About A and C, so A and C, no matter what their values are, they can't really affect the control flow of this guy, right? Because the conditional only depends on B. And so A and C can basically be whatever values you want, and everything is still the same. So here we can't say anything, so we just say nothing. And we can't say anything here. So in this particular example, we can only say anything about B. Okay? Yeah, any questions about that before the next part? Okay, so the next question asks, is it possible for this program to give you a SIMD utilization of 20%? So yes or no? So why would that be? Yeah, was that you? Okay. Yeah. Yeah, that's right. Yeah. So 20% is actually lower than the minimum possible SIMD utilization, right? Because it's either, so as we talked about, it's 100% if all of them execute the same type of code. And so this is already the worst possible case. So no, it is not possible to yield a SIMD utilization of 20%. Okay. So the next part of this question, so this was also like, if yes, what should be true about A, B, and C to be 20%? And so we said that it's not possible. So if no, explain why not. And this is because 9 out of 40 is the minimum, right? 9 out of 40 is already the minimum. You can't get any lower than that. So part D of this problem asks, is it possible for the program to have a utilization of 100%? So I guess I basically already said yes, it is actually possible. So yeah, so if yes, what should be true about A, B, and C in order to get this 100% utilization? I don't know, one of you guys want to answer? Or? Yeah, for B, for the array B, right? So all of B has to be either less than 0 or greater than or equal to 0, right? And so, yeah.
Just in one warp, there can be one warp all negative, and then another warp all positive.
Yeah, that's true. Yeah. That's right. So, like basically all groups of 32, right? Yeah, so all these groups of 32 of B have to be, so you have the right idea though, like, yeah, so all the threads in the warp have to do the exact same thing. And again, A and C don't affect the control flow at all, so there's really no constraint on those at all. Okay, I think that's actually it for that question, so any last questions for there? Oh, okay, cool. Where's the Oh, okay. No, we don't need another out of order. Let's do vector. It's gonna suck. You'll work. God, look at you. Okay, so this is a question about vector processing. Okay, so again, there's a little bit of setup, and we're telling you like what sort of constraints we have on this system. So we have a program that's running on a vector machine with these latencies for these types of instructions. So let's go through them. So we have a load and store, which take 50 cycles for each element, and they're fully interleaved and pipelined, like basically fully pipelined for all these instructions. We have an add that takes 4 cycles per element, a multiply that takes 16 cycles per element, a divide which is 32 per element, and then a right shift operation, which just takes 1 cycle for each element. So, okay, we're making some assumptions here. So we're saying the machine has an in-order pipeline, so it's not doing any funny out-of-order business. The machine supports chaining between vector functional units. So if you guys remember, chaining is when like one functional unit is complete. As soon as it processes an element, it can immediately send it to the next element. So you don't have to wait for the entire vector to be processed before starting the next operation. Okay? So in order to support a 1 cycle memory access latency after the first element in the vector, the machine interleaves vector elements across a bunch of different memory banks. And all vectors are stored in memory with the first element mapped to bank 0, the second element mapped to bank 1, and so forth. Okay, so we have a number of memory banks, and each sequential like load element goes to a different bank. And so each memory bank has an 8 kilobyte row buffer. Okay, vector elements are 64 bits in size, and every memory bank has 2 ports, so that 2 loads and stores can be active simultaneously. But we also have 2 load store functional units available. Right, so each one can operate for different instructions. Okay, so the first question asks us, what is the minimum power of 2 number of banks required in order for memory accesses to never stall? And we're assuming a vector stride of 1, so you're not skipping elements in the vector. Yeah, so who has an idea for this one? Yeah. Okay, well, so you said 32, so why 32? That's actually true. So I think this one was a little open to interpretation because we have 2 load store functional units. So if you have, just one, if you're thinking about just one load store functional unit and you're able to access both banks, both ports for each bank, then yes, that's right. Because the access latency is 50 cycles, and in order to hide 50 cycles, you need more than 50 banks, right? Because you can do 1 per cycle. So if you're thinking about both load store functional units going at the same time, then the answer is a little bit different than that, because now you have 2 functional units constantly doing loads, so you're doing 2 loads every cycle. And so the idea here was that each memory bank has 2 ports so that each functional unit can be active at the same time, and so 1 per. So if that was the case, then you would need to support 50 available ports per functional unit. So you'd need more than 50 banks, right? So in that case, you would need 64. So it'd be 32 banks for just 1 functional unit using both ports, or 64 for 2 functional units being able to use like 1 port each, for example. Yeah. So we're going to say 32 for one functional unit, 64 for 2 functional units. Okay. So the second part of the question asks, so the machine with as many banks as you found in part A executes the following program. And again, we're assuming the stride to be 1. So let's go through the program real quick. So we have a load to the vector 1 from some input A. And then we have a vector load to 2 from some input B. We have an add of vector 1 and vector 2 into vector 3. We have a multiply of 3 and 1 into 4, and then a right shift of vector 4 with a shift of 2 going into the register V5. So we say you're given that it takes 111 cycles to execute this particular piece of code, right, with the given hardware assumptions that we talked about before. So we're asking, what is the vector length? So again, so this is another case where we have to consider like a timing diagram, because each of these instructions will take a different amount of time to execute, and some of the dependencies will have to wait on the previous executions to finish, right? So we have to kind of draw this out. And we're given the final number of cycles, and so if we do everything in terms of a variable vector length, then we will eventually have an equation for, a number of cycles in terms of the vector length will equal to 111, and we can solve for the vector length. So let's go ahead and try and draw this out. I wish this was bigger. Like, there's more room. So let's see. So we have first the vector load into V1, right? So we're going to say the vector load here is going to first, first we're going to fetch the vector load instruction. So that's going to take a cycle. Then we begin executing the vector load. So we have a cycle for execute. And now we know that up here, the vector load has a 50 cycle latency for every element, right? And then after that, it's fully, like as a vector machine, you get one result every single cycle, right? And so we're going to have execute. We're going to have like 50 of these cycles. And then eventually the first load is going to come back. And so we're going to start having a bunch of our loads return. And so we're going to have like a series of loads all the way. And we're going to have our vector length of loads. And so the thing is that this is variable because we're going to put this in terms of V. So what's going to happen here is we have fetch, we have execute. The first load comes back on 50 cycles. And then we have, until it finishes, it's going to be 50 plus vector length minus 1, right? Because the first load came back after 50 cycles. And then you have every cycle, every other load coming a cycle after that. So we can say that this is, what's the best way to draw this? Not really sure. I wish there was like a bigger paper. So let's have this be like, oh yeah, let's draw it on there. I don't know. Maybe we just draw it like this. So we're going to have the vector load, and then, oh, maybe, yeah, sure. So we have like the fetch here, which is like 50 instructions for the latency originally. And then we're going to have a latency of vector length minus 1 until this one finishes, right? And then we have the second load instruction. And for the second load, we're loading into a different register, but we do have 2 load store functional units. And so that'll basically just go to the second functional unit. And since we have enough banks to keep everything busy, we don't have to worry about bank conflicts. So this is going to start a cycle later. And so we have 1 cycle here, and then we have another 50 cycles. And then we have another V length. So I'm just going to call it V. So we're going to have another set of V minus 1, which executes here, right? Then we have our vector add instruction. So the V add into V3 depends on V1 and V2. So since these functional units are chained, because this machine supports chaining between functional units, we can immediately begin using the first element as soon as it's ready. Like we don't have to wait for all these loads to finish. So the first element comes back for V1, because this is a V load into V1, comes back here, and then for V2 it comes back here. So from here we can begin using the result. And so right after it's done, we have some latency for the vector add itself, and then again we get 1 vector per cycle, 1 vector element per cycle. And so here we have vector add takes 4 cycles. So we have a 4-cycle latency. A 4-cycle latency, and then we execute V minus 1, different elements. Then the next instruction is a vmul. So we have a vector multiply into register 4, and this one is dependent on V1 and V3. And V3 is the add we just completed. So it can't start executing until the first element of the V add is complete. And so after the first element is back, 4 cycles later, we can begin the multiply. And so the first element for the multiply takes 16 cycles, right? So we have a 16-cycle wait. And then after that, we have V minus 1 other elements to wait for. And the final instruction we have is the VR shift. So this is a V write shift. And it's just the exact same thing. This takes 1 cycle. So after 16, when the first element is back, we take 1 cycle for the first element, and then V minus 1 up until here. So we're basically saying the overall execution of this program takes 111 cycles, right? So what vector length results in that sort of number? So if we go through and add up all these latencies, we're basically trying to figure out the time from here to the end of execution, right? So first we have this flat delay of 50. Then we have the extra delay of 1 for the next instruction. Then over here we have a delay of 4. Then we have a delay of 16. Then we have a delay of 1. And then we have a delay of the vector length minus 1. So this is plus v minus 1, right? And so this lot should hopefully be like, oh, I'm sorry. Yeah, so there you go. Okay. Yeah, so the 50 represents the first part here. And then we have the latencies of each individual instruction after. So we have an extra 1, a 4, a 16, a 1, and then the v minus 1, okay? And so all of that together should hopefully equal some multiple of 1, 1, 1, right? So these ones cancel each other, and then you end up with, 50. We have 71 plus v equals 1, 1, 1. So that results in v equals 40. Right, so our vector length for this example is 40. And so what is the vector length? 40 elements. Okay, that's what results in this sort of execution time. And sorry? Oh, yeah, go ahead. Yeah, the other ones, these guys don't really matter so much, right? So the fetch for this instruction, you're saying. So fetch and decode. So that's a good question. Nothing was specified about fetch and decode in this question. They just told you that vector load and vector store are 50 cycles for each vector element.
So do we assume 1 cycle because that's the least amount we need?
1 cycle for what?
For fetch and 1 for decode? Because we have
So
1 cycle.
yeah, so in this particular example, I think it was lumped basically into this 50 cycles, like the first instruction. But yeah, I don't know. What do you think? So I think this is not good. Yeah, like in a proper test question, this would be well specified. These are just like the practice questions that we came up with to discuss here. It really should be. So in that case, I guess you would model the extra fetch and decode stage here before it enters execute, and then you'd have like an extra +2, and we would have given you 113 instead of 111. Yeah. Okay. Yeah, but that's absolutely right. Like, we should take that into account. Okay. Yeah, I mean, any other questions about this example? No? Okay, so I guess we can go to the second part. So we've determined that this vector length for this example is 40, right? So the question asks, if the machine did not support chaining, but we could still pipeline individual, like independent operations, how many cycles would be required to execute this exact same program? And so again, just to be sure, like it does say show your work, and a lot of the exam questions will also say show your work, because if you show the steps, then we can figure out what went wrong and maybe give you a lot of credit, even for things that didn't work out well. So we're assuming now that we can't chain operations, which means that while the first vector load and the second vector load are independent because they're two different registers from different addresses, and we have 2 different functional units. The ones that are dependent, like the vector add, cannot actually begin until the vector load is fully complete. So we incur extra penalties where we can't just overlap these latencies anymore. So we end up drawing like a different timing diagram now. So it can't fit all of this on the same page. It's so unfortunate. Okay. So we're going to start with the vector load again. So we're not going to take into account the first fetch and decode, but they really should be there. Okay, so we're going to say 50 for the first element, right? Okay, and then we have a delay of v minus 1 until everything's complete. For the second one, it's the same case because they're independent of each other. So we can begin this at 1, which, yes, we can begin this 1 later, and then again we penalty of 50, and then v minus 1 until it's complete, right? So the complexity comes with the add now. So the original add depends on v1 and v2, so both of these guys. And so we cannot begin the add. We cannot begin the add until we have completed our vector load entirely, right? Sorry? Yeah, so the first element, even if we have the first element by the time we're here, since there's no chaining, we can't begin using it. Like we have to wait for the whole operation to complete. So the whole operation is not complete until here, right? So now we can begin our actual vector add. And so we have a 4-cycle latency for the vector add, and then we have v minus 1 latency until everything is complete. Okay? And so after the v add, we have a v mul, which takes in v3, basically using the result of the v add, right? So we have to wait till that's done. So we have the v mul, and so again, we can't start processing the first element until everything's done. So here we begin, and we have a 16-cycle latency for the, that was right, yeah, the 16-cycle latency, and then v minus 1 until everything's done. And then the final instruction is the v archive. And so this one uses v4, which is the result of the mul. So we can't start until that happens. And so we can't start here. We just have 1 cycle latency, and then v minus 1, right? And so now that we have the timing diagram here, we basically just go up and add everything together with the number 40 for the v here. So this results in 1 plus, let's see, 1 plus 50 plus 4 plus 16 plus 1 plus 1, 2, 3, 4, 4 times v minus 1, right? Okay, so that's our expression for it, where v is 40. Do you just have the number for it? I don't feel like adding. See, this is 20, it's 70, 72 plus 4 times 39, 36. Yeah, it is, yeah. Yeah, 228. Is that right? Yeah, okay. So, so that we have this number. So, you see, like, yeah, like chaining makes a dramatic difference because you don't have to wait for the full vector length latency. And so especially if the vector was like hundreds of elements long, it would be much better to have a system that does this. And so now part C says that it becomes a lot more complicated, actually. So the architect of this machine decides that we need to make the memory system simpler. And we can't support, having 32 or 64 banks of memory. So instead, we reduce the number of banks by a factor of 2 from the number we found in part A. And because the loads and stores might now stall due to bank contention, an arbiter is added to every single bank so that pending loads from the oldest instruction are serviced first. And the question is, how many cycles does the program take to execute now with the reduced number of banks, but still with chaining? So this assumed that they were tied to a port. Okay. Yeah, that's right. So, okay. So what we're doing here is that we're reducing the number of banks, and when basically that affects these two load instructions first here, right? So we have vector load of A and vector load of B. And we can't, so once the vector load instruction begins, we're assuming, at least in this problem, that once a vector load to a particular register begins, it's tied to a specific port. So we have now fewer banks than we have the latency, but once the first vector load instruction begins, it's going to start consuming stuff from port 0, and vector 2 is consuming from port 1. Okay, we're going to make that assumption here, and so basically we just end up drawing like yet another timing diagram, and so we start again with the vector load, except this time we pay the 50 cycle latency, but we don't get all of our operations back. We only get the number of operations for the particular bank that we have. I guess this is a better way to show it, right? Should I use that? Yeah, okay. So, it's really complicated. So, what's happening? Okay, so previously we were assuming that we had 64 banks, right? So that we could service both load instructions at the same time and continuously keep loading one per cycle. So now we only have 32. And so when we issue the first series of vector loads, there's a 50 cycle latency until the loads begin coming back. But we can only issue 32 loads at any given point in time. So after the first load comes back, we only get 31 loads here until we have to issue the next series of loads, which takes another 50 cycle latency. So we have 50 more cycles, and then we get the rest of the data elements here. And the rest of the data elements here would be, so we get 1, and then, so we've already done 32, so we get 7 more. Right? Does that seem reasonable? So the first load instruction takes all this amount of time because, is that right? No, you can overlap this with this, yeah? I think you don't have to wait for this before you start the next one though, right? You can start issuing as soon as the port's free. Is that true?
So you wait 50, and then you start issuing the other.
Yeah, so you don't wait 50 here again. Yeah, so okay, so not waiting 50 like this and 7. As soon as the first one comes back, the port is again free, so you can begin issuing more loads here. So the 50 actually starts waiting from here, right? And so you wait 50, and then you get 7 back. Yeah, okay. So yeah, so basically the port is busy until you start getting the first load back, and then you can start issuing more loads again. So the first vector load takes this amount of time, here, up until here. And you've got back 31 plus 1 plus 7 plus 1, so all 40 data elements that you're interested in. Then we have vector load 2, and since we're assuming that it uses the second port from the banks, it doesn't overlap with this at all. So I'm sorry, it entirely overlaps with this. So we have our 1 extra cycle of latency, and then the exact same thing happens. You wait 50 cycles, you get back your 31 elements, but at this point you've started issuing the next section of 50 cycles, and you get back the rest of the 7 elements. Is that end of class? Yeah, okay, so I guess we'll be posting these online with the solutions as well. So you guys can go through them yourself, and if you have any questions, you can email us or see us in lab session or whatever works for you, yeah? All right, thank you.